So now suppose that you have a wire that's arranged in the shape of a loop, and there's a continuous steady current flowing around it. Let's just assume. So what we have basically is, well, I wanted to make that black. We have a loop, right, of some radius, we'll call capital R, and if there's a current, let's say flowing around it in that direction, then there must exist a magnetic field, right, outside and inside of this current loop of this wire. Using the right-hand rule, you can see that, well, the current is going, let's say, upwards on the outside. So outside it's going like that, and then inside it's going down. It's actually curving, right? It's curving around. So for the magnetic field, looks like that. What's the magnitude of the magnetic field at a point inside this loop, right? Specifically, what's the point, or what's the magnitude of a point right at the center? We'll call that point P again. Well, we can use the Biot-Savart law again, which is of the form mu naught I over 4 pi times integral of ds crossed with r hat over r squared. Right? That's always the Biot-Savart law. And, well, if we want to find the field at point P, we have to evaluate that cross product. Right? I know it looks hairy, but it's really not. Okay? So this loop, this wire, is of some total length. It's of the circumference of that circle. We'll say total length of, well, 2 pi capital R. But we have a bunch of DS's, right? A bunch of wire segments that comprise this loop. And each of those segments are of equal distance to point P, if P is in the center. And that means that they're both, or they're all, a distance capital R away. But more specifically, they all have some R hat. Oops. Let's do it on the other side. They all have some R hat vector pointing towards that point P in question. So when we evaluate this cross product, 4 pi, we're integrating all of those DS's. So it's integral 0 to the total length S, which we just know as 2 pi capital R. And the cross product becomes magnitude of the first times magnitude of the second, which is 1 because r hat is a unit vector, times sine of the angle in between over r squared. The angle in between, I've tried to draw it a little bit askew. If that's a circle, that's 90 degrees. So in this case, theta equals 90. So sine of 90 is 1. And so what we have is mu naught I over 4 pi times the integral from 0 to the circumference of that circle of, well, 1 over r squared. Right? The ds, we actually have to input that, right? Or rather, take that into account. We have 1 over r squared. What is, well, we can't exactly take 1 over r squared ds, right? What's that lowercase r? That lowercase r is always the distance from the wire segment creating the field to the point in question here. So that distance is then capital R. Right? And that's a constant. So really that can be pulled out too. 4 pi r squared. And now we just have integral 0 to 2 pi r of ds. Well, it's pretty easy. the pi's go away, factor of 2 goes away, and a factor of r goes away. So we have mu naught I over 2r. And that's it for the magnitude. The direction is, well, downwards. So we'll say down. That's it.